This is A. Somaiah, working as Assistant Professor in the Department of Mechanical Engineering. Welcome back to the course of Fluid Mechanics and Hydraulic Machines. And the topic is the Pelton wheel turbine and the required fundamentals for understanding the turbines is impact of jet on vanes. So in the previous class, we have discussed regarding the classification of turbines and working principle of turbine. So we have given the number of examples to understand different type of turbines as per their classification. And now we'll see the impact of jet on vanes basics in order to understand the working proportions and velocity triangles of a Pelton wheel turbine and the remaining turbines too. So yeah, basically the Pelton wheel turbine is nothing but it's a impulse turbine. First thing is impulse high at the low specific speed and tangential flow turbine, which is invented by Laser Pelton. So this is named after Laser Pelton, American engineer who contributed much to its development in 1818. So it's named after Laser Pelton. The turbine is known as Pelton wheel turbine. And the basic the classification as per different types of classifications. So how do you introduce, otherwise how do you express the Pelton wheel turbine? The Pelton wheel turbine is a high at low specific speed and tangential flow turbine and low efficiency turbine also. So the runner consists of a circular disc with a number of buckets evenly spaced around its periphery. So that is a runner. So which is composed by a number of evenly spaced the hemi-ellipsoid curved vanes. So here we can see the buckets and runner and the entire the schematic this sectional view of a Pelton wheel turbine. The Pelton wheel turbine is a impulse turbine. That's why after taking the liquid from a penstock of a reservoir, then penstock, then at the exit of a penstock there will be a converging nozzle in order to convert into a kinetic energy, and in which there is a spear valve. This is known as spear valve. The spear valve, the purpose is to regulate the amount of flow onto the turbine buckets. So therefore, the spear valve can be regulated with the help of spearhead outside of the turbine. And in actual installations, it is connected to a governing device. So according to the fluctuations, according to the changes in your demand outside of the powerhouse, based on that, so the governing mechanism will regulate the amount of flow onto the turbine with the help of the spear valve. So therefore, spear valve will be connected to a governing mechanism in order to cater the varying purposes outside. So then is a tangential flow because the center of all the bucket center of the bucket is a pitch circle. The pitch circle diameter, for the pitch circle, the center of the jet or spear valve is tangent. Therefore, it's a tangential flow turbine. That's why we should not call it as an axial. It's a tangential flow. So axial means it may not pass through. It is axial maybe to the rotation of a shaft, but it may not pass through the tangent of a circle. That's why it is a tangential flow turbine. It will have a number of backward curved vanes, like the number of vanes is equals to d by 2d plus 15. So minimum number is 15 and the capital E is diameter of a turbine or a pitch diameter. So now small d is a dia of jet. This is small d. Small d is a diameter of jet and pitch circle diameter d by 2d. So plus 15. So that will be equally spaced over here. Turbine periphery, runner periphery. So then there is a scroll casing in order to guide the water onto the tail race. Otherwise, the water will be splashed away. In order to control the splash of water and to guide onto the tail race, there is a spiral casing. The spiral casing will guide the water onto the tail race. But then there will be a shaft. The shaft is connected. So connected to the runner, these two are coupled. So whenever the water with heavy force kinetic energy, because pressure energy and potential energy will be converted into only kinetic energy. With this high kinetic energy, whenever the liquid is impacting on a blade, the blade is a double hemi ellipsoidal, so in the middle there will be a splitter. So whenever the water is hitting on a splitter, the water will be divided into two halves, two equal halves, so that the maximum amount of the energy possessed by the liquid can be utilized by the turbine for the generation of electricity. That's why it has to be splitted into two halves. But then there will be a slit at the end of a bucket. At every end of a bucket, there will be a slit. So, in order to empty the water as early as possible, and not only that, it should not hit the previous bucket, so that the water should be quickly. It will after working on a turbine, it should be get emptied. So, the splitter purpose is to make water the incoming jet into two halves, and by utilizing the complete energy by the turbine, then it will be get dispersed onto the spiral casing. From the spiral casing to it come onto the tail race. So due to this force, while the turbine buckets are moving, as this is connected to rotor will be connecting, and it is connected to a shaft. The shaft will be rotating. So due to that, there will be a the mechanical energy will be developed. So this water energy input is half mv square. The water energy possessed by the water in the previous class we have seen rho GQH, the inlet energy of a water. But all the energy is converted into kinetic energy in case of a impulse turbine. So by utilizing this energy, this is rotating, means the mechanical power will be developed. So therefore, the power available at the shaft divided by the power developed by the rotor by rho GQH or half mv square is nothing but hydraulic efficiency. So this is the purpose of the scroll casing, and how it works is as it is impulse turbine, it is converting entire energy into only kinetic energy. So there will be number of there you can install not only single jet, uh, it can be used, or it can be installed so many multi jets also. So one more jet here, another jet is here, and one more jet is here. So the multi jet also based on the requirement. So the number of jets can be installed. So we have seen with only single jet impulse turbine, a Pelton wheel turbine. So, but a number of jets based on the requirement, and there will be empirical relations are there. Based on that, we have to utilize, you have to accommodate the number of jets required. The buckets have shape of double semi-ellipsoidal cups. So here in this picture, we can see that see the double semi-ellipsoidal cups are there. In between, there is a splitter. This sharp edge is known as a splitter, and there is a notch at the exit. So in order to remove the water as early as possible, also in order to avoid the splashing of water onto the previous bucket, there is a notch at the exit and a splitter to make inlet jet into two halves. Divided into two symmetrical parts by sharp edged ridge known as splitter. So one or more nozzles are mounted so that each directs the jet along the tangential to pitch circle for an axis of blades. The jet of water impinges on the splitter, which divides jet into two equal halves. After flowing around the smooth inner surface of the bucket, leaves at its outer edge. The buckets are so shaped that the angle at the outlet lip varies 10 degrees to 20 degrees, so that the jet of outer deflects 160 degrees to 170 degrees. So the deflection angle we will see while deriving the expression for work done. So angle of deflection. The advantage of having double cup shaped bucket is that the axial thrust neutralizes each other being equal and opposite. So So whenever there is a splitter, it is dividing two halves. So therefore, neutral it will become neutralized. Otherwise, there will be imbalance, so that there will be damage to the rotor. So axial thrust neutralizes whenever it is equally made into two halves. The back of the bucket is shaped that as it swings downward into the jet, no water is wasted by the splashing. At the lower lip bucket, lower lip of the bucket, a notch is cut which prevents the jet striking the preceding bucket. The preceding bucket, as we have discussed in the previous slide, the deflection of water towards the center of the wheel. So for low heads buckets are made of cast iron, and high heads buckets are made of cast steel, bronze, stainless steel, etc. In order to control the quantity of water, striking the runner nozzle fitted at the end of the penstock, provided with a spear valve having streamlined and which is fixed at the end of the rod. When the shaft of Pelton wheel is horizontal, not more than two jets are used. If the shaft is vertical, we can use six number of jets. So based on shaft disposition, according to the classify, the shaft can be disposed horizontally, otherwise it can be placed vertically also. So based on the position, we have to use adapt the number of jets required. So if it is vertical, it can be adapted with the six number of jets, multi jets. In this sectional view, we can see the notch of the bucket and double hemi-ellipsoidal or semi-ellipsoidal bucket, the shape how it is and how it is coupled to a rotor. The shaft is coupled to a rotor, the perfect key, and while the jet is coming and it will be splitted into two halves. In this diagram, it can be seen. So and after heating over here, so after making into two halves, it becomes axially neutralized. So axial thrust becomes neutralized, and this half can be left like this, and the remaining half will come like this, flash like this against the spiral casing, and it will be guided into the tail race. A casing is made of cast iron fabricated steel plates. Is usually provided for Pelton wheel to prevent splashing of water, to lead water to the tail race, and also act as safeguard against accidents. Large Pelton wheels are usually equipped with a small brake nozzle, so which when opened directs a jet of water on the back of the bucket, thereby bringing a wheel quickly rest when after shutdown. So there will be a brake. It will be utilized as a brake by impacting a jet on the backside of the bucket. So in order to derive the work done developed by a rotor, or the power developed by a rotor or turbine. So we need to understand the velocity triangles whenever the jet is impacting on a curved vane, how the velocity triangles will be developed, and based on that, how do you derive the force along x, similarly force along y, etc. So the force can be calculated if the force is known, force into distance. So then there we can calculate work done, force into distance. So that's why we need to understand the velocity triangles, how it is generated. So whenever the assume is not for Pelton wheel, in general, whenever a bucket is backward curved bucket is located like this. When the water is striking at the one end, at one end tangential to the curved surface in this direction, not axially emitting. So, but I am applying from one end. So in this direction, the jet is kept in the tangential to the inner curved surface of a bucket. So therefore, the jet coming out of the nozzle is V1. So V1, that is nothing but a jet velocity. V1 is nothing but a jet velocity. So whenever it is striking with V1, the blade tries to move. So therefore, the U1 is blade velocity. So due to V1, there will be blade velocity, that is U1, V1 and U1. blade velocity and jet velocity. Okay. Now, if you resolve the V1 into horizontal and vertical components, we will have another two components. The vertical component will be known as flow velocity and the horizontal component is known as while velocity. Horizontal component is while velocity. While velocity which is responsible for developing of the work done. Okay, the flow velocity is a perpendicular component. So after obtaining the jet velocity and it can be resolved into two components and it will give the while velocity and the flow velocity. Flow velocity is perpendicular to the while velocity. While velocity is the responsible for the work done. Okay, then this U1 is indicating the blade velocity because of V1. So now the angle between the jet velocity and blade velocity is alpha. That means the inlet jet angle at inlet at inlet velocity triangle alpha is the difference. Sorry, the angle between V1 and U1 is alpha. Alpha also known as inlet velocity at inlet the jet angle, inlet jet angle. Similarly, after drawing the triangle, after knowing these various components, and there is a relationship between the jet velocity and blade velocity is VR1. Therefore, that is known as relative velocity. So, this is a jet velocity through which water is impacted. So, from this nozzle. Therefore, this is jet velocity V1 due to jet velocity, blade will be moving with U1 and there is a relationship between these two. Relative velocity VR1 will exist. Okay, there if you resolve, then we will get another two components. One is horizontal component is VW1, vertical component is VF1. So the angle between V1 and U1 is alpha inlet jet angle, and the angle between VF1, the horizontal component VW1, and with VR1 is theta. So that is inlet blade angle. It is also known as inlet blade angle. So these are the various components on a inlet velocity triangle. So after moving through the blade, inner surface of the blade, so the jet velocity V1 becomes V2. The same velocity due to frictional losses, the same velocity can't be obtained. Therefore, the velocity will be reduced. The line will be plotted like this. So V2 due to reduction in the velocity due to losses. So V2 is there. This is V2, and so there will be a blade velocity due to V2 is U2. So I got two components V2 and U2, and the relative velocity between this U2 and V2 is VR2. So I got these three components now. And if I resolve again, I will get the horizontal component and vertical component. Flow velocity is always the vertical radial VF2, vertical component VF2, and horizontal component is VW2. So like this, I got similar parameters at outlet velocity triangle also. So therefore, this is inlet velocity triangle, and this is outlet velocity triangle. So here, in the outlet velocity triangle, due to the reduction in the velocity, the same lines at same positions we can't find. The relative velocity will be same, but V2, the velocity, jet velocity or absolute velocity will be reduced. VF1 is always perpendicular after resolving the jet velocity into two components. Now, alpha and theta at inlet velocity triangle, it gives inlet jet angle and inlet blade angle. Similarly, at outlet, the beta indicates outlet jet angle. Otherwise, the angle between V2 and VW2. V2 and VW2. Similarly, phi is the outlet blade angle between U2 and VR2. U2 and VR2. Alpha and beta, inlet and outlet jet angles. Inlet and outlet jet angles. Similarly, so theta and phi are blade angles at inlet and outlet. So remaining are all velocity components. Some of the parameters are absolute velocity. Some of the velocities are blade velocities, etc. Relative velocity, while velocity, flow velocity, so on. But the while velocity at inlet and outlet, so which are responsible for work done on the blade or work developed by the blade. So based on while velocity. So the transfer of work from jet of water to the buckets may be determined by applying the momentum equation. So the figure shows velocity triangles at the tips of buckets of a Pelton wheel turbine. Okay, jet. Sorry. So let V1 we have gone through V1, U1, VR1, all these parameters. And we know alpha, beta, and theta phi, VW1, VF1, etc. We have gone through. We have understood all these parameters. Now VW2 and VF2 are the component of the velocity object V2. So these are horizontal and vertical components in the outlet velocity triangle. Similarly, VW1, VF1 at in inlet velocity triangle. VW2 is also known as velocity of while at outlet. So similarly, now I want to find out the force applied due to this impact object. So that will be mass of water per second into change in velocity, rate of change of momentum. So rate of change of momentum. So initial velocity with which it strikes jet strikes when at inlet is VR1. So VR1 with the V1 and VU1. So with the relative velocity is due to V1 and U1. With this relative velocity, it strikes the when at inlet. Therefore, inlet velocity is VR1. The component of velocity, direction of motion. In the direction of motion, at inlet is VR1 cos theta. So this is the VR1 cos theta. So that is nothing but VW1 minus U1. That is VR1 cos theta. VR1 cos theta is nothing but VW1 U1. VW1 minus U1 is VR1 cos theta at inlet. Similarly, at the outlet velocity, the minus VR2 cos phi. So this is the outlet velocity in the outlet velocity triangle. This component is the relative component of relative velocity at outlet is minus VR2 cos phi. As this is moving in the opposite direction, we have to consider negative sign. So that is minus VR2, the VR2 cos phi. So this is nothing but minus of U2 plus VW2. So this equation, this line is summation of U2 plus VW2 minus. So that is nothing but as it is in the negative direction, VR2, that is VR2 cos phi is minus U2 plus VW2 or minus VR2 cos phi. Sorry, not theta, it's a phi. So now we can apply in the force expression, rate of change of momentum. So the rho a V1 and change in velocity is VW1 minus U1 at inlet velocity, and outlet velocity is minus of U2 plus VW2, minus of minus. Then we will have rho a VR1 into VW1 minus U1. So the U1 becomes U1 and U2 both are same, therefore you can cancel. So as along x direction, the force applied by the jet on the vane is rho a VR1 VW1 plus VW2, rho a VR1 into VW1 plus VW2. So because the rate of change of momentum is nothing but the mass for time into inlet velocity minus final velocity. So here mass is again, so here density is nothing but mass per unit volume. Then mass becomes density into, this is equals to density into volume. So here density is rho, volume is A into VR1, volume. This is nothing but volume. So that is mass per second into inlet velocity minus final velocity. So therefore we got Rho A VR1 VW1 plus VW2. Whenever beta is 0, whenever beta is 0, so here beta is less than 90. Whenever beta, not 0, whenever beta equals to 90 degrees, then the VF2, VW2 becomes 0, VF2 becomes V2. So this is a condition whenever beta makes an angle of 90 degrees. When VW2 is 0, so this can be cancelled. Rho A VR1 into VW1 is a force about x direction. So when beta is 90 degrees, only these three components will have. This becomes beta. This is VF2 equals to V2. So then VW2, here there is no VW2 component, it becomes 0. So this is entirely U2 only. Then VR2, and this is phi beta. So therefore, in this condition, the Fx equals to rho A VR1 into VW1. So other than this, if it is greater than 90, then the velocity triangle will be drawn like this. So this becomes beta. Whenever it is greater than 90, this is phi. So in this case, again this is VR2 only. V2, VF2 is always perpendicular, and this is U2. So U2, and this is VW2. Therefore, here we can see U2 minus VW2, U2 minus VW2 is the outlet velocity component. So rho A VR1 into VW1 minus VW2. So after applying initial velocity minus final velocity, so VW1 minus U1, this we have derived, but when beta is greater than 90, so it will be U2 minus VW2 from this velocity triangle. So therefore, when beta less than 90, when beta equal to 90, when beta greater than 90, there are three different equations we are getting Fx. So in general, that can be written as rho A VR1 into VW1 plus or minus VW2. So in this case, whenever the problem based on the given problem, if it is less than 90, then we have to go for plus. If it is greater than 90, we have to go for inserting minus. Okay, whenever it is equal to 90, we can eliminate VW2. So these three equations can be remember based on the angle of beta. Work done after knowing the force about x direction by the application including the, so whenever you are applying the rate of change of momentum, so whenever is applied on a the jet is applied on a vane due to that force, the jet due to force applied by a jet that will be moving, so there will be a rate of change of momentum whenever considering all these parameters at inlet and outlet. Okay, we can derive the force expression. Okay, force is nothing but a rate of change of momentum about x direction. Okay, so then after knowing x, then we can calculate the work done. Work done is nothing but a force into distance per second. So that's why we are calculating the force. After knowing force, the distance moved in the direction of x is u. So Fx into u. Then we will get rho A VR1 into VW1 plus or minus VW2 into u. This is nothing but work done. So this is the work done by a turbine, by a blade. So whenever work done is there, you can find out where work done per second per unit weight. That expression is the ratio of work done per second. That is rho A VR1 VW1 plus or minus VW2 into u. This is the work done per second. Then a ratio of weight of fluid striking per second. So weight of fluid is specific weight. That is specific weight into value. Then the rho g into A VR1. So from this expression we'll get 1 by g into VW1 plus or minus VW2 into u. This is the work done per second per unit weight. The efficiency of a jet is output by input. So we know the output is rho A VR1 VW1 plus or minus VW2 into u. This we have derived, and the input is half mv square. Only in the kinetic energy, in the form of kinetic energy, we are giving the input. Therefore, half mv v1 square So in the simplification, we'll have this expression: efficiency is output by input. Output is this one, and input is of mv square, where m can be written with rho a vr1. Okay, so m is nothing but density into value. Therefore, rho a vr1. So vr1, why not v1 means vr1 is the responsible with which the jet is striking, because v1 due to v1 there will be u1. The relationship between v1 and u1, there is a relative velocity vr1 with which the jet strikes the van. Therefore, vr1 will be considered. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.